Okay, Professor.
Yes, we would like to continue today, and I would like to first assign you the homework. What is our set number? 6. So I will start with, if you recall, we derived the face portrait for the undamped free vibrations. And if you remember, this is like this. This is x, this is x dot, okay, or velocity. And we found that this is usually an ellipse. Sometimes it is a circle. Okay, x. Or it could be x here and x dot there. It's not important. I just showed you both possibilities. Now, this is not yet a homework, of course. This is just a reminder. Now, derive the face portrait for the underdamped free vibration case. Means zeta is smaller than 1. So we would like to have a connection between x and x dot. And then, yes, choose parameters numerically and draw the portrait. Okay, best is by computer. Okay. So today is 128:09. And now the next topic is as follows. We discussed single degree of freedom system, 1 degree of freedom system. Okay. We did not finish it yet. We did not finish. However, we dealt quite a lot with 1 degree of freedom systems. Then there is also 2 degree of freedom system. For example, just imagine this is a mass, M1, and this M1 is connected to some M2, and this is connected to the ground. And for example, this M1 is also connected, for example, to the ground. so that is K1, K2, K3, and everything is vibrating in this direction. Okay, a longitudinal direction. Then there could be 3 degrees of freedom system. So this system has 2 frequencies, 2 natural frequencies. Omega 1 and omega 2. Okay, imagine this is a ground, and this is connected with this. This one is connected with this, and this is connected with this. And imagine each of them is connected with the ground. So imagine K, 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 K. So this also, so that is M, M, and M. Imagine masses even are equal, it's not important. So here we have 3 natural frequencies. Omega 1, omega 2, omega 3. Etc. There could be n. So pay attention, this system I built very interestingly. I mean, at least I connected, first of all, each mass to each other. So look, please, this mass is connected to this one and to this one. But this mass is also connected with this one. And each mass is also connected with the ground. Okay, so that was a special thing that I did, yes. In order to answer, so you have to speak loud because there is some noise here. Yeah, it depends on the values that are here. For example, if this is M1, M2, M3, so it depends upon M1, M2, M3, and K. Depends on the system parameters, naturally. And there could be n degree of freedom system. So imagine this, look please. This is connected, this is connected, this is connected, this is connected, then this is connected to this, then this is connected to the ground, and each of them is connected to the ground. This is connected to this, and this is connected to the ground. So this is M1, M2, etc., M sub n. N is positive integer. And we have various Ks, K1, K2, K1, K2, etc. Then, very beautiful thing happens, that this system has n natural frequencies. So that is omega 1, omega 2, etc., omega sub n. N natural frequencies. And there is a whole theory how to obtain this. I have the transparencies. Usually I'm teaching this n degree of freedom systems immediately after 1 degree of freedom system. However, I decided that this, maybe it's better for us, for our purpose, to immediately jump into the cold water of infinite degree of freedom systems. And later, if we have time, we will come back to n degree of freedom systems. Okay? N degree of freedom systems is usually well covered in every textbook. Say 2 degree of freedom system especially is very well covered. Not n degree of freedom system, but 2 degree of freedom system is covered in any textbook, whichever book you will buy. It is there 2 degree of freedom system. Much less is given about infinite degree of freedom system, but that is where action is. Okay? So therefore, we go to our next topic. And what is our next topic? What is the number? 15. And what is the title? I will tell you. Vibrations of beams. So that is like, this is a relatively more advanced course. So this is like to teach a child, to count 1, 2, 3, and then immediately go into integral and differential calculus. So that is what we are doing. But you're smart guys, so therefore everything will be easy, and I think that it is very easy anyways. Okay, so the question is, what is a beam, first of all? So beam is a 3-dimensional structure. That is main observation. That is something that has dimensions. Beam is a 3-dimensional structure. Okay. Now beam has following dimensions. One is called length, something that is bigger than the others. Oh, thank you. Actually, I thought that I could survive.
There's red and there's like blue.
Yeah, that is it. Yes, thank you. And when are you going to make this here?
I'm still working
Okay, thank you. I would like to trust you. Thank you.
I'll let you know.
Thank you. Okay, so one is called length. Then there is L2, which is called width. And the other is called depth or height. So we have width, depth or height, and the length. So this, what is here, depth and width, are forming this cross section. This is a cross section. So this is perpendicular to the axis. Okay? Now, beam is a structure where one dimension is much greater than 2 other dimensions. So L1 is much greater than L2, and L1 is much greater than L3. So beam is a structure where one dimension is much greater than 2 other dimensions. For example, this thing is not a beam, this one. Why? Because it has 3 dimensions now, thickness, so width and depth, and we don't have any one dimension that is much greater than other 2 dimensions. So this is, for example, not a beam, but we have it here. Okay? This could be considered as a beam, for example. There is 1 dimension length, which is much bigger than cross-sectional dimensions. Okay? Now, the dimension which is biggest is called length. So that is how we find what is length. Could I define different? No, the one that is biggest is called length. So beam is a 3-dimensional structure in which one of the dimensions, length, is much greater than other 2 dimensions. Now this is not sufficient actually for the beam to be called beam, for the structure to be called beam. Beam, we call a structure beam if predominant deformation is perpendicular to the axis along the length. bar is also like a beam, but if predominant deformation is longitudinal. If deformation is longitudinal, then we talk about a bar. If deformation is perpendicular to the axis, we talk about the beam. Okay? Now I would like to say that, so this is a three-dimensional body. What does it mean, three-dimensional body? In three-dimensional body, we have some, say, displacements, say W. That is a displacement. Displacement is perpendicular to the beam's axis. So for example, as a result of the forces, this beam bends, and we get a displacement. This displacement is function of x, y, and z. It is a function of the point in the beam. Okay. We will do first the strength of materials approximation. What is the strength of materials approximation? We will reduce three-dimensional body to one-dimensional body. And that is called BE theory or Bernoulli-Euler theory. So that was done by Daniel Bernoulli and Leonhard Euler. A long time ago, approximately 730. Okay, that is a year when they developed, approximately. Okay? So actually mathematicians developed engineering theory that is still in use. It's a very interesting fact. So the question immediately is asked, why do we need an approximate theory? This is an approximate theory. Bernoulli-Euler theory is an approximate theory. Why do we need an approximate theory? Why not to use general elasticity theory? Okay, answer is approximate theory is simple. We will use very simple theory. Now, it is not only simple, but also catches very well what is happening in reality. So that is amazing. Okay, let us start with these beam vibrations. So transverse vibrations of beams. So we first have this beam, and you may want to see this beam. And this beam, pay attention, we take some cross-sectional area at distance x, and this element is dx, this element, this length of this element is dx. And displacement is w. This beam undergoes displacement, which is called w. Now, pay attention. This beam this element is vibrating. Because it is vibrating, so there is some term that is associated with vibration. And that has to do with mass. What is this mass? Density, that is a rho, density, material density, times cross-sectional area. So that is this beam's cross-sectional area. That is width times depth, if it is rectangular. Times dx, so then it is a volume. A times dx is a volume. A times dx is a volume. Rho is a density. This is an acceleration. So this is a dynamic force, like mass times acceleration is acting upon this beam. Then what we get is as follows. We are writing equations. Now we know one connection from strength of materials, and if you don't remember, we are taking it for granted, and that is as follows. Moment, so what are things that are acting here? Bending moment. Now here is bending moment mz plus dmz dx dx. So that is a change of the moment. Because when I go from one cross-sectional area to another cross-sectional area, this moment changes. So if moment is here mz, here is mz plus dmz dx dx. Here is shearing force, Vy. This is a shearing force changed, Vy plus dvy dx dx. Okay, do you want me to enlarge it? Enlarge this picture? Maybe like this. Please make this picture to yourselves. Oh, yes, this is why, yes. So that is a good question, actually. The only reason I wrote here partial is, and here partial, because W depends upon X and also depends upon time. So there are two variables, time and axial coordinates. Therefore, we have partial derivatives. This is Vy, this is Vy plus dvy dx. Now, the thing that I said that we are taking from strength of materials without proof, but that was proven to you several times, actually. Moment is connected with the displacement. And that is EI times second derivative of W with respect to X. E is modulus of elasticity. Please write down. I is moment of inertia. Now, we take some of the forces in vertical direction. When I take some of the forces in vertical direction, there is this Vy, then there is this Vy plus dvy dx dx, and there is this force. So together will be like this. Sum of the forces in y direction. Vy minus Vy minus dvy dx dx minus rho a dx d2w dt square. That is sum of the forces in x direction. Please write down only the first equation. Now we also write the second equation, which is, look, sum of the moments with respect to this point. Please denote this point. And then we have, look, please, this guy does not give me a moment because this passes through this point. So only this gives me a moment. So, but I said moment in this direction is positive. So therefore, this guy gives me a negative moment, minus Vy dx. But this moment and this moment cancel each other, mz, but this stays. So it will be dmz dx equals 0. So we have two equations. Say it again. Okay, so we have two equations. We have forces in this direction naturally. So we wrote down some of the forces in this direction. Then there is, can you return the picture? Because I probably pressed somewhere in a wrong place. Maybe. Sorry, I probably pressed somewhere. Oh, it's there. Thank you. So, look, there are but there are no horizontal forces. Because this beam, we said, is predominantly something that undergoes displacement perpendicular to the axis. That means that there are forces in only that direction, not in the other direction. Say it again. Oh, this one. Okay. This one would make a moment also, but pay attention. This one is already with dx. So if I will multiply from here by this load, will be dx divided by 2. So will be dx times dx divided by 2 will be dx squared divided by 2. Dx squared divided by 2 has a smallness which is bigger smallness than the other quantities, therefore it should be neglected because it is much too small. Delta x squared. We are keeping only elements with delta x. So actually I thought that when I started to talk about, I thought maybe you are asking me about forces in axial direction. Okay, now, so look please. Here this Vy and Vy will be gone. So there is a derivative of Vy. Okay, derivative of Vy. But derivative of Vy is connected actually with second derivative of the moment. So therefore, we are getting an equation. Okay? If I will substitute minus Vy from here into here, that's first. If I differentiate this, I will get second derivative of the moment, and it should be substituted here. So I will get second derivative of the moment with respect to x squared dx equals minus rho a dx d2w dx squared. So, sorry, that is what we get. Okay, now we are using what I was talking about. That moment itself is a EI times second derivative of W with respect to X. So this guy should be substituted here. And the dx's are gone. Because dx here, dx there. So we get, look, that is a governing differential equation. Second derivative of EI second derivative of W plus rho A d2W dt squared equals 0. So you may want to write down, this is a general equation for beam vibration. And this equation was known already, as I said, to Daniel Bernoulli and Euler in 1730, approximately. Euler graduated, he got master's degree in age of 15. In age of 18, he started to look for the job, could not find the job in Switzerland. I mean, he was looking, because in Switzerland, the jobs were chosen by lottery. So everyone was excellent. So they did not have a competition checking the resume and how good you are. Everyone was extremely good, so they were choosing by lottery. So he applied once, he did not get the job. He applied second year, so he also did not get the job. So at that time, Daniel Bernoulli, also a Swiss person, became a professor in Russia. So he wrote him, you know what, if you don't find the job, I will offer you the job in Russian Academy of Sciences. But I will offer you the job not in mathematics, but in physiology. So Euler said, that's no problem. I will study physiology because it takes several months to get to Russia from Switzerland. So in these 6-7 months, I will study physiology and will be professor of physiology. So when he arrives to St. Petersburg, on that day, professor of mathematics died, just on the same day. And Euler was appointed as a professor of mathematics because they had a need, urgent need, in mathematics professor and not in physiology. Physiology would be just an additional job, so I mean, additional professors there. So he became a professor of mathematics. Daniel Bernoulli was one of his teachers before in Switzerland, so they were talking to each other and discussing things. That is how theory of beams came into being. So generally, E is a function of X, modulus of elasticity. What does it mean? It means we can have two materials, say one material and then second material and then third material. So therefore, modulus of elasticity could be changing. Now, yes, sir? Modulus of elasticity. Okay, I will explain what this is. E modulus of elasticity. So when I will take a specimen and apply a force here, some force, and cross-sectional area is A, then we can form stress, which is F divided by A. Now the initial length is L initial, final length is L final, so we can also form elongation, L final minus N L initial. Or better yet, to find something non-dimensional, L final minus L initial divided by L initial. Okay, just one second, maybe I'm too fast. Let us put everything together. Then this sigma, if I will put this on one diagram, in the beginning at least, like until some point, this relationship is linear. Sigma equals E times epsilon. So how to find E? It's very simple. Just apply the load, then find at some point, this is a value of epsilon, epsilon 1. This is a value of sigma 1. Okay, and sigma 1 divided by epsilon 1 equals E. This is how to obtain from experiment. So this is like modulus of elasticity or Young's modulus. Okay, Thomas Young. No. 1676 he gave this formula. Okay? This we know. Now, so generally all of these quantities, mass density changes, cross-sectional area changes. So for example, here we can have rho 1, here rho 2, etc. So this is generally partial differential equation with variable coefficients. This is partial because there is x and t. It's a differential equation because unknown function is under derivatives with variable coefficients. Okay, now we will consider simplest possible case. Simplest possible case is E is constant, rho is constant, cross-sectional area is constant, and moment of inertia is constant. So why don't we write down simplest possible case? Then please look here. If these EI are constant, they can be taken out of the parentheses, out of differentiation sign, and we will have here forced derivative with respect to x. So we get EI d4w dx in force power plus rho a d2w dt square equals 0. Okay, so this will be our equation. We will be dealing with this equation quite a lot. Later in the course, we will deal with variable cross-sections, variable modulus of elasticity, etc. We will cover beam vibrations very widely. So I'm not just dealing with simplest possible cases. 1 degree of freedom system was necessary in order to introduce to the ideas what is happening, natural frequency, etc. So this small w now can be represented, let us check whether it's correct or not, as capital W of x, some function big W of x, which depends only upon axial coordinate, and something that depends upon frequency, omega. Do you remember in free vibrations, I had this natural frequency, omega. And I found this natural frequency, omega. Okay, here I'm saying, okay, maybe there is omega here also. Maybe in this problem, there is some natural frequency, omega. If it is, then its solution should be like cosine omega t or sine omega t, or just cosine omega t plus phi, or sine omega t plus phi. It's okay. Anything could be, any trigonometric function can be assumed. Now, if this is so, if indeed this is a solution, then it is a magnificent solution because look, for 1 degree of freedom system, I did not have W of x. I just had cosine omega t plus phi. Here, the only complication is that function of time is multiplied by function of axial coordinate. But otherwise, the whole thing stays as it was before. Nothing has changed, so to say. Just this, that was also, this product was also suggested by Bernoulli and Euler in the same year when they suggested it. So let us substitute this equation 2 into equation 1. This is equation 2. So this is actually assumed for. Assumed for. Maybe it does not work, but we will see that it does. So we substitute this function here, we get forced derivative of capital W times cosine. Then here, when I differentiate cosine, and I get minus omega squared, and capital W equals 0. So the equation that I get is as follows. For capital W, EI d for W dx in force power minus rho a omega square capital W equals 0. Now, the question is just put there, what are we looking for? What we are looking for? We don't know several things. We don't know omega. We wrote cosine omega t plus phi, but how much is omega? Is omega 1, omega 2, omega 1.5, whatever, or 0.1, whatever value. So we don't know omega. And second thing that we don't know is capital W of x. We don't know W, we don't know omega. We will find both. We will find both omega and W. And we will get very exciting results. I'm promising. So now I will divide this differential equation by EI. So I will get then rho a omega square over EI times capital W equals 0. Okay, this rho a EI I know, omega square I don't know. This is a fourth order differential equation. It makes sense to denote this like alpha in force power. Alpha is not known also because omega is not known. So alpha is not known, but we will find it. Alpha in force power. So we will get an equation, force derivative of W with respect to x minus alpha in force power, W equals 0. If you have any questions, please stop me immediately. If I need to explain 2 times, I will explain 10 times, I will explain 100 times, as many times as needed. So this is what? Homogeneous, because there is no right-hand side. Ordinary differential equation. Now I will deal also, this is also homogeneous boundary conditions. I will write later boundary conditions. It depends on boundary conditions, how this beam is connected, how it is restrained. Now we are looking what we want to find. We want to find alpha or omega. It is called eigenvalue. I will later explain why such an unsuccessful name, I would say, eigenvalue. Eigenvalue is a composition of 2 words. One is value, which we do know. Eigen comes from German word. German word which means own. Own value. Own. O-W-N. Or private value, so to say. And suddenly when you print, say when you type, then suddenly computer does not recognize it as an English word, and it says correct. So this is, English speakers just fell in love with this German expression. So therefore they are using this word. Mathematicians, of course. You cannot tell to someone, you are my eigenvalue. This does not happen usually. Okay, so what we want to find? We want to find alpha such that W of x is not identically 0. Because if W of x is identically 0, then there is no vibration. This beam does not vibrate. If the displacement is everywhere 0, then there is no vibration. I want to have some vibrations. So W must not be 0 identical. It should not be 0 everywhere. So find any alpha, such that W of x is not identically 0. This means 3 lines means identically 0, these 3 lines. And this means not identically 0. Means these 3 lines means everywhere 0. Beam naturally could have some points where displacement is 0. For example, if that is simply supported at the ends, then in these 2 points displacement must be 0. So, but it should not be 0 everywhere, because if it's everywhere 0, then there is no vibration. Okay? So pay attention. This is not a simple problem because, look, W is not known and alpha is not known. Okay? It's very strange. I mean, at first look, it should be looking very strange. We don't know alpha, we don't know W. So how are we going to find the solution? Yes, this requirement is very important. We want to find any alpha for which this equation does not have a zero solution. But whatever solution will be, we will accept, just it should not be zero. Yes, so we would like to put then, this is an ordinary differential equation. Because it is an ordinary differential equation, I substitute W equals C, capital C, in power Rx. R is something that we would like to find. I substitute this one here, and I get. So fourth derivative will be C R in fourth power E in power Rx. But then we cancel by C and E in power Rx. We get R in fourth power minus alpha in fourth power equals 0. So this R cannot be any R. R should be such that R in fourth power minus alpha in fourth power equals 0. Now, this is a difference of squares, because this is R squared squared minus alpha squared squared. So difference of squares can be written as sum of these numbers times difference of these numbers. You agree? So from here, R squared plus alpha squared, R12 equals plus minus I alpha, because this is R squared plus alpha squared equals 0, means R squared equals minus